We're in the middle of K dot P theory. So we started constructing this last time, this, where is it? 4x4 or 8x8 really, Hamiltonian. It breaks out into two 4x4 blocks. So the basis is three bonding p orbitals that form the valence band edge at k equals 0 before you turn on the spin orbit coupling, and the anti-bonding s orbital that forms the conduction band edge, and one of those for upspin and one for downspin. So you got four orbitals, two spins, so you get these 8 basis states which form the basis for this 8x8 K dot P Hamiltonian. If you recall what this K dot P Hamiltonian was, you had a P squared over 2m plus your crystal potential V of R plus this new term, this, K dot P term plus this H bar squared K squared over 2m term. And these two new terms disappear at k equal to 0. And at k equal to 0, you're just left with P squared over 2m plus V. And so at k equals 0, these states are the exact eigenstates if you ignore spin-over coupling, which we're putting in explicitly. And then once you start turning on k, you start coupling these basis states, and that's how you evolve your band structure. And so one of the most important things in this theory is this matrix element of the momentum operator, because that is your K dot P term. Kane used this notation to define what he calls P, and writes his Hamiltonian in terms of P, which then you find these values for P in databases, for example. And once you find them, then you can go ahead and calculate things like optical absorption coefficients. So this is the generic form of our 8x8 Hamiltonian. It's got these two big 4x4 diagonal blocks we call G, and this block could be all for spin up, and this block is all spin down, and so the gammas couple spin up to spin down. These are the things that are coupling the different spins. So the only thing that's going into the gamma is the stuff that couples the different spins. And the G's, those G blocks, we said break up into 3 different blocks. One block, we started the G1 block is coming from your K dot P term. This block is coming from your spin orbit coupling term. And this is coming from coupling to the anti-bonding P orbitals, and we'll talk about that today. And we take that into account just using perturbation theory, because we don't explicitly include these anti-bonding p orbitals into the basis. Otherwise, instead of 4 orbitals, would have 7 orbitals, and then would have a 14, and then you double it for spin, then would end up with a 14 by 14 Hamiltonian. People do that, but if you don't need to, you don't want to. And so then we went ahead and we looked at G1. So this is the form of G1. For k equal to 0, all these terms disappear. These terms here, they all disappear. And these terms here at k equal to 0, right? And you're just left with the diagonal terms, which if you ignore spin orbit coupling, they are just the conduction band edge and the valence band edge. Right, so k equal to 0. This just shows you that this basis is the eigenstates if you ignore spin orbit coupling. I said Hamiltonian is just diagonal. This EV prime we talked about is shifted because when you turn on the spin orbit coupling, you get this kind of splitting, and the true valence band edge is raised up by delta over 3. So you initially define EV prime as the actual valence band edge minus delta over 3, because when we turn on the spin orbit coupling, it's going to raise it up by delta over 3. All right, so that's G1. So this is taking into account the K dot P term. It's actually, I guess you would say, it's taking into account all this stuff I wrote down in green, the K dot P term, and just P squared over 2m plus V. So that's all included there. Then we have the spin orbit stuff, which looks just like what we did with the tight binding Hamiltonian, since we're using the same orbitals, just in linear combinations, px, py, and pz, and s. This whole thing goes on the diagonal. This is one of the G terms, this guy. goes into your diagonal block, and this is a Hamiltonian that couples the up spin to the down spin. This is coupling the two different spins going in that off diagonal block. And I factored out the constant terms out here, so you gotta, these non-zero terms are multiplied by the negative delta over 3. So that was the G1, the GSO, and I guess that's as far as we got. And lastly, we need this thing that couples to these higher p orbitals that we're really not including explicitly in the basis. And in U and Cardona, they refer to these as a gamma 4C. They use a lot of symmetry and symmetry notation in that text. And so we're going to refer to these, the bonding states, which are the ones that we explicitly have in our basis, just for notation purposes. I'll call that, say, XB, and the B is for bonding, and then the antibonding, I just call it XA for the antibonding orbital. So the antibonding orbital would be up above the first conduction band. We'd call that the second conduction band. I don't know if you remember these pictures we drew back in the beginning. Our P state orbital, our S orbital, and when we bring these atoms close together, you get this splitting. You get some really low state. This splits off into these 3 closely spaced bands. This, for the direct gap material, this becomes your conduction band edge, and this splits off into 3 antibonding p orbitals. So our basis that we're explicitly including are those states right there. And the ones that we're now including through perturbation theory are these guys up here. Those are our 3 antibonding p orbitals. So these would be like our p bonding, and these would be our p antibonding, our S antibonding, and that's it. That's the only stuff we're doing right now. So these matrix elements that we're not explicitly including, and that we're worrying about right now, are like this: XB, the bonding, PX, XA. So these kind of matrix elements are not necessarily equal to 0, and we want to include them, their effect, somehow. So these guys, which I'll just write generically of the form, are some p bonding orbital, your momentum operator from that k dot p term, and your p antibonding orbital. They're taken into account using perturbation theory. So if I just look at this matrix element, say a bonding p orbital with our k dot p term and the same bonding p orbital, that's equal to 0. Well, because both orbitals have the same symmetry, and p always makes something antisymmetric. So p changes the symmetry of whatever it acts on, so the integral is going to be 0. And we already went through this, like the only non-zero matrix element with those four basis states that we include, the S and the 3 P's. The only non-zero matrix elements you get are like SPXX, SPYY, and SPZZ. So this gives you nothing, but let me define the matrix element between these two bands as, just to call it and give it a name, I'll call it HIJ. And then because of coupling to the higher bands, which we're not explicitly including, but they do have an effect, and you take it into account using perturbation theory. So the modified matrix element becomes this term, which is 0, plus the stuff that's coming out by taking into account those higher bands. So summing over the bands of these antibonding orbitals of the matrix element between the state you're interested in, which would be that XB up, and whatever that band is in your sum over the energy difference. And so, just like when we were doing perturbation theory before, the farther away the band is, the less important the less important it's going to be, right? Because you get that energy denominator term. So in this case, EI is the band of interest, which is your valence band, right? And EN is that second conduction band. So this is really, if we want to give this a name, I guess first of all it's going to be negative, right? Negative E, sort of your second band gap. And if we go back to our little picture, here, it would be the distance from, right, this is your band gap, EG, and this is what I'm calling EG2, this difference here, calling it your second band gap, the next set of states up after the first conduction band. Again, there's only going to be a certain subset of these matrix elements which are non-zero. So we've got non-zero matrix elements between these bonding p orbitals, which are our basis, and these anti-bonding ones. And so you've got 6 of them, and they are, so X bonding P, Y, Z anti-bonding Y, B, P, Z, X anti-bonding. Like every combination where no one of the terms is the same X, Y, or Z. And these are all defined as equal to IQ, where Q is another parameter that you're going to find in databases, back in appendices of articles and such. And so, given that, if you go back and look at this expression, what we wrote down here, and using these definitions for the non-zero matrix elements, then we can write down what this is in terms of Q. And that second band gap, which is known just from experiments, optical experiments, you'll get that immediately. So this renormalized matrix element, taking into account these higher bands, is equal to, and the denominator, well, that energy difference is the same. For those 3 antibonding bands, I just have an X antibonding, Y antibonding, and Z antibonding. Is minus EG2, that energy difference we talked about. And so if you go back and look at the possible non-zero matrix elements, that's just equal to, and all this stuff out front is just defined in another parameter that you can find for different materials, M times KY squared. This is going on the diagonal term between the px in itself. Right? Before, if you looked at the diagonal terms, you just had, well, that's the spin orbit stuff. On the diagonal, we just had these, EC, EV prime, EV prime, EV prime, and now those are going to get modified by all these terms that are quadratic in K, right? So because we have this thing up in the numerator here, up here, right? That's a matrix. If I and J are the same, that's a matrix element squared. Right? If I and J are the same, that's just a matrix element squared. Because HIN is the complex conjugate of HNI. That would just be a matrix element squared, and we're taking the matrix element squared of K dot P, so you're going to have a K in there, so you're going to get a K squared out of every one. And we're going to get mixed Ks, like KX comes KY, and it's going to get kind of nasty looking. But these are the matrix elements that go into that last G matrix, G2, which, when we sum them all together, gives us the final G matrix. So here's that term, and without going through it, this is sort of standard stuff you can find in journal articles. It's standard form for the G2. It's kind of messy. It's going to be a 4x4 Hamiltonian, and every term is quadratic in K. Oh, it's so much easier. There we go. There it is. There's your G2 matrix, and there are all the terms. Your 16 terms in the G2 matrix. It's a completely full matrix. There's no non-zero blocks, except for the fact that if you have a crystal with inversion symmetry, then all these terms that you see with those red arrows are zero. So the first row, you'd end up with all zeros, and they're all generally small, even if you don't have perfect inversion symmetry. So even for the zinc blend like gallium arsenide, they're ignored. So in fact, you would have zeros going down the first column and the first row. You know, when we originally derived our K dot P Hamiltonian, we had our P squared over 2m plus our V of R plus the K dot P term, and we had a K dot P term, some stuff out in front of it, and we had this H bar squared K squared over 2m. There's something out in front of our K dot P term. Right, and so finally, this term is now finally showing up here on the diagonal. Right, it's on the diagonal of each, on each diagonal, you've got that H bar squared K squared over 2m, which is just your quadratic dispersion of the particle in the vacuum. But you've got all this other stuff showing up on the diagonal from coupling to those higher anti-bonding p orbitals. And then you've got some other cross terms also, which get to be really messy when you take the next step, which we'll talk about in a bit. So, as I said, for your a crystal with inversion symmetry like silicon or germanium, all those B terms are ignored. For the zinc blend, they're generally ignored also. And if you notice, there's a bunch of constants there that we really haven't defined. So these are sort of always determined empirically. All these constants that you see, like n prime, l prime, what else? I guess that's a prime on the diagonal. A prime for the s orbitals, L prime for the p orbitals. So all these things can be found in the literature. It's not often easy, but depends on how well studied the material is, whether you're going to find them or not. And I guess I also drew this little, in my notes, this little cartoon. So these are the bonding orbitals that you're taking into account explicitly. And these are the matrix elements. These are the anti-bonding states, which you're not including as part of the basis. And these are the matrix elements between the bonding and anti-bonding states that you're including via perturbation theory. And physicists say you're sort of integrating out those extra coordinates out of the problem. But that's what we're doing. So, one would be like H1n, and this would be Hn1, and well, you saw what we do, how we include that using perturbation theory. So as I said, those constants can be found in the literature in two sort of classic articles. What we now have is we've got our three G blocks, G1, G2, G3. They're all 4 by 4. You just add them all together to get the total 4 by 4 block, and you've got two of them, one for spin up, one for spin down, and you now finally have your full 8 by 8 matrix. But before, let me just say something more about these parameters. I said you can find them in the literature. You can, it's not always that easy because there's two sets of notation that are used, and you often have to be able to go back and forth between them. So everything we've done up till now has been using the notation of Kane, but you'll find that a lot of the literature is in terms of the notation developed by another guy, Luttinger. And there are something called the Luttinger parameters, which are related to the Kane parameters. So often in data books, you'll find the Luttinger parameters. And you need to often to be able to go back and forth if you're working with the Kane model. So what are they? Well, the Luttinger parameters are simply 3 parameters, gamma 1, gamma 2, and gamma 3. And they also use parameter EP, so in the data book, you may be looking for P, you'll see EP, and this is defined as 2 m0 over h bar squared times the magnitude of this matrix element squared, and this P is equal to times the thing that we've really been using. So I mean, this is just the way things got defined historically, and this is the way you'll often find stuff in data books. So we had a Hamiltonian with these other constants like L prime less equal to plus P squared over the band gap. M is equal to minus h bar squared over 2m0 times 1 plus gamma 1 minus 2 gamma 2. N prime is equal to the last parameter. We had A prime up in the corner on the diagonal element for the s orbital. So all this has to do with these other guys, L prime, M, and N prime are all for the p orbitals. So to get A prime, this is how you get A prime from known stuff. So M0, the bare mass, over the effective mass of the conduction band, which is known experimentally, that's your conduction band effective mass, is equal to 2 m0 over h bar squared times A prime, which is the parameter we are after. That's the band gap plus 2/3 of that spin orbit splitting, delta, over the band gap. So those are relationships between the Luttinger parameters and these parameters used in the Kane model, the L prime, M, and N prime. And it just depends who you're reading, what parameters you might find. Okay, so given you have the form, the full 8x8 matrix now, you're able to find all the parameters you need. So we now have our full 8x8 Hamiltonian K-dependent Hamiltonian matrix is equal to our G blocks, our 2 G blocks, which are functions of K, and the 2 gamma blocks, which are not functions of K. Right, this is going to be the form of your Hamiltonian. And so each one of these blocks is 4x4, which we explicitly constructed. And you put it all together, you have your 8x8 Hamiltonian, and of course this G is the sum of all the G's we just calculated. Okay, so that's gives you your full 8x8 Hamiltonian. And so once you have that thing, then you do exactly as what we did before. Once you have a Hamiltonian, you go ahead and you calculate the eigenvectors and the eigenvalues. So exactly as once you have h of k, as we did before, right? We calculated h of k in a completely different way with our localized orbital, but once you have an h of k, then you go ahead and you choose a value of k, and then you go ahead and you solve your eigenvalue problem. You solve for the eigenenergies, right? That's an 8x8 eigenvalue problem that you send off to MATLAB, right? So an 8x8 matrix, you're calculating the 8 eigenvalues of that matrix. You just send it off to MATLAB and you do eig, and it will give you back your 8 eigenvalues. So you put it in a loop, right? You loop over k. You define some k matrix. You loop over k, and you choose, say, a direction along the kx axis. You loop, you update, for each k, you update that 8x8 matrix, you send it in the eigenvalue, and so for each k, you're going to get 8 values for your energy. Right? So E, K, say you're going along the 100 direction, and so at each K, here's a K, I'm going to get 8, a lot of duplication because of spin, like at the conduction band, the upspin lies exactly on top of the downspin. So it'll kind of look more like 4 with some splitting in the valence band, right? And I choose another K, and I'll get another set of 8, but really like 4 with a little bit of splitting. And then you just draw a line through it, and that's how you get your bands, right? Something like that, and you just plot it out. So you just loop over K, plot all the points, and you just connect them up, and you have your E versus K relationship.
So they're not continuous.
What's not continuous?
Are they discrete values, or are those just the...
Well, they're on the computer.
So they have to be discrete.
Well, whatever you put them in your array, yeah, they're going to be a discrete set of points.
But are they discrete?
No.
Are they discrete or continuous?
K is continuous.
Continuous.
But
Can we use 0 because we're using perturbation and the K shouldn't be around.
yeah, I just happened to be reading about that. So for gallium arsenide, I never really knew like exactly how accurate this was, but I just happened to come across a book on this recently. So for gallium arsenide, using the standard, 8-band K.B model, they say it's good within about 10% of the Brillouin zone around gamma, which means, so if you have, I'm running out of room here. So, if you have your full Brillouin zone, it's going to be a very flat band here, going from pi over A minus pi over A. It's only good within 10% around K equals 0, so whatever 10% looks like, a rather small region there. We're saying where this band model is valid, right? There's no Fermi level that I do. This is just how far this band model is valid in K.P. In our localized orbital, it was valid over the whole range. This K.P, the way we're using it, is not. There is stuff that they call full band K.P, but they use like 14 bands to do it. And it looks periodic. I don't quite understand how it's done, but the way we're using it here, it's only valid around gamma, and that's why it's a fairly simple Hamiltonian, and if you're doing optoelectronic calculations, 10% around gamma is all you need. Okay, so that starts to bring us up to optoelectronics. And so far we have an 8x8 Hamiltonian, which is really just a Hamiltonian that describes the bulk band structure. And now your advisor tells you to go out and design a laser. And most lasers aren't made with bulk material anymore. Do you all know sort of how a laser is constructed?
Can't you use either like a ruby or like a...
Okay, like the laser in your pointer. There's no freaking ruby in your laser pointer, right? Those were the very old-fashioned lasers. Okay, so the question is, in a laser, any modern laser is going to be a quantum well. Is going to have some kind of quantum well in it. I mean, this is where this theory is used heavily in designing various types of lasers. And so the simplest type, you can draw very sophisticated things, but the simplest concept is you need a p-n junction, right? A laser has electrons and holes. You need recombination. You need the electrons to recombine with the holes to generate photons. So you need a p-n junction. So on one side it needs to be p-type, and over here it needs to be n-type, and in the middle some stuff has to happen. So I want to have a quantum well. Okay, this would be the band structure of something that looks like a quantum well laser with a single quantum well in it. So this is my conduction band edge, my valence band edge, my Fermi level. And so over here it's p-type, over here it's n-type. So as I apply a forward bias, right, so this is n-type, means I have a lot of electrons here in the conduction band. right, all piled up, not many holes. And over here, this is p-type, so I got a lot of holes sitting here in the valence band. And I apply a forward bias, so forward bias means I raise up the bands on this side, so this is forward bias when I apply a forward voltage to my p-n junction, to turn on my p-n junction. And when I do that, I'm going to start sending electrons into this quantum well. I'm going to start sending holes into here, and then they're stuck, right? They come up, and now they got to, for this hole to continue, it sees a barrier. For this electron to continue on, it sees a barrier. They're stuck in those quantum wells, and it's a direct gap material, so they're going to happily recombine. And so they're going to this electron is going to fall down, meet its hole, and give off a photon. And that's the concept of a laser or an LED. LED laser, whatever. Using this optical recombination in a direct gap material. So we have a Hamiltonian for a bulk material, and here you have something that's operates in a quantum well. And how do you possibly use this Hamiltonian to model something like this, where you have material that's a function of position, you've got boundary conditions, you've got finite length scales. So I mean, in the bulk, everything is a plane wave. There's no, if you look anywhere, the wave function is just, the underlying periodic part times this e to the I k dot r. You take the magnitude squared of e to the I k dot r, it's 1. There's no modulation of, any of the eigenstates, no spatial modulation. But now, in our quantum well, if I look at the envelope, these are just like particle in a box states. Now I have an envelope that looks like, the first state, second state, even odd. And the same with the holes down here. I have envelope, this, just particle in a box states. Right? So there's an envelope. And, the wave function is going to go towards 0 at the edges, and it'll be sort of maximal in the middle, because it's a particle in a box state, right? And so how the heck do you model this using this 8x8 bulk Hamiltonian that we just derived? I mean, if you go back and you think about our localized orbital Hamiltonian, it's like, it seems kind of obvious. So if we take a moment and think, well, in our tight binding, so we go back and think about our tight binding Hamiltonian. We never really did this. But you can see how it's easier to think of in your tight binding model. In our tight binding model, we explicitly put in the atoms. And we reduced it because using just looking at one unit cell, reduced it to like a 2x2 problem. But we can explicitly put in all the atoms we like. We know all the matrix elements coupling every atom. So if we would just want to extend this to a really big structure, we can. And then your matrix, just for this line of atoms, and then we'd go back to our 1D chain that we did at the very beginning, right? If we do a 1D chain, then we just get the on-site energies. And here, the on-site energies can all be different because I could be applying some kind of potential to the device. And in a nearest neighbor model, you just have the coupling between nearest neighbors. And so it's kind of easy to imagine how you would take into account spatial variation in your tight binding model. This was exactly the model we had for our chain of carbon atoms, for our polyacetylene. This was exactly what we had for polyacetylene. When we applied periodic boundary conditions, and we only needed to look at 2 atoms, But you could just extend it and look at as many atoms as you want, put them explicitly in your Hamiltonian, truncate it with hard-wall particle in a box boundary conditions, send it off to your eigenvalue solver, and just solve it. And it would give you these sort of standing wave type states. And that seems kind of conceptually clear. But what about this? Because we don't have any. We just have a bunch of K's and stuff in our Hamiltonian. We don't have these explicit picture of orbitals on atoms and matrix elements coupling them. Well, there's a little magic trick.
What do you want to calculate?
I want to be able to use my K dot P Hamiltonian to model a structure like this.
In which parameters do you want to find? Do you want to calculate the transport or?
I'd be happy to just say start by calculating the say particle in a box states in that quantum well. We don't even talk about transport till next quarter. Right? This 8x8 Hamiltonian is for a bulk material. There's no sense of any finite dimensions in there. Now, if I want to do, or if I want, how do I deal with a heterointerface, a heterostructure? I have two different materials slapped together in this K dot P model. In the localized orbital model, it's easy. I just have like gallium, arsenic, and then aluminum. Put in an aluminum atom, arsenic. No problem, because I explicitly have all my atoms. But what about K dot P? How do I include spatial variation? That's the question. And the answer is this trick. And again, we go back to it was really spelled out as best as I know. And this is the article that we really used when we implemented this for research. Again, the same article by Gershoni. It all goes back to this. Everyone references this. Okay, and the trick is to deal with a heterostructure, some spatial variation. Let's say I want to deal with spatial variation along, let me define an axis here. So let me call this my x. So I have spatial variation along the x direction here. And everything in the YZ plane, everything's uniform. Right? In Y and Z, nothing's happening. So you only have spatial variation in x. And this is what happens when they really grow these heterostructures using MBE, right? They grow an infinite plane of one material, then grow another material on top of it, et cetera, et cetera. So there's no variation in this direction, only in the growth direction, which I'll call x. And so if you want to take into account variation in that direction, or in any of your x, y, z directions, you take kj, where that j would be x, y, or z, and everywhere we had it before, you replace it by minus I d xj, where xj is just a shorthand notation for writing x, y, or z. So specifically, just so I don't confuse the heck out of everyone, if there's spatial variation along x, then wherever you had a kx, that becomes minus I ddx. Or if you have spatial variation along kz, along the z direction, then wherever you see a kz, you replace it with minus I ddz. In our Hamiltonian. And so if you recall, let's just take the simple G1. So if we look at the G1 matrix, we had EC. Okay, so I'm explicitly going to use have it varying in the x direction. So then G1 becomes this, P ddx, I P ky, and I P kz minus. Okay, so the only difference, so because we have variation in the x direction, right, I replaced the kx terms, with this minus I ddx in our matrix. And you think, oh, that's just great. I got derivatives in my matrix now. Now what? How do you send a matrix with a derivative in it off to MATLAB? That's the kind of thing a professor would come up with. Anyway, so yeah, the question is, what do you do with your derivative? You got a matrix with a derivative inside of it. It's like, probably never seen that before. Well, the way we deal with it is, if you go way back to the beginning of the course, we had an effective mass equation, right, way back when, and we discretized that derivative. And so, since you got to solve this on the computer, you're going to have to discretize this derivative and deal with it using finite. So, you think about, this derivative, right? This matrix is acting on something. We have this vector of C's. It's acting on which, and now you're discretizing this on a grid in X, right? You're taking your x-axis and you've discretized it on a set of points on your x-axis. You have some spacing, I'll call it A, right? Uniform spacing in between. And for each one of these points now, each one of these points will be represented by the full 8 by 8 matrix, which is now only a function of ky and kz. So this is still 8 by 8. Each one of these points is an 8 by 8 matrix. And they're going to be coupled by these finite difference terms. So again, the structure of the Hamiltonian is going to look like an 8 by 8 H for site 1 coupled by some coupling matrix. It's just always this tridiagonal form. The 8 by 8 for site 2, the 8 by 8 for site 3, again coupled by these coupling matrices, which we're going to work out in a second. Right, so these are all 8. Each site is represented by an 8 by 8 matrix. So for every site, you have an 8 by 8 that are now only a function of the k's that you did not, or the k's, in this case, ky and kz. There's no more kx because you're now working in, you call it real space in the x direction and k space in the y and z directions. Okay, so what do we do with this derivative term? Well, we do exactly the same thing we did to it way back when we discretized the effective mass equation. So you take your derivative, and it's going to be operating on something. So C sub n is the, you've got some vector on the right-hand side, your C1, C2, blah, blah, blah. I guess I'm not sure what my n stands for, if it's that index or what. It's not the position index. Well, let me go through with it because time is getting short. So if we discretize it using finite difference, exactly like what we did at the beginning of the course, it becomes Cn, where I is now my site index on my discretization grid. That would be, right? So now I is the index of my discretization grid. I I plus 1, I minus 1. So this is C, I minus 1, I plus 1. And so what this is telling you is that this first derivative term, if you go back and look at our structure of this thing, this first derivative term is coupling. If this is that central site, this is that central site here, that derivative is coupling this, back to the site behind it and to the site in front of it. So this guy is being coupled, and we end up with something that looks like this nearest neighbor model that we've been dealing with from the very beginning. Right? Each site is coupled to the one in front of it and to the one behind it. And it's this nearest neighbor model, which gives us this same block diagonal form for the Hamiltonian. And it was the same thing we had in tight binding when we were doing linear chains and such. Except now every site is a matrix, and I guess we've run out of time. So I guess we'll finally get to the calculation, the optoelectronic stuff next time. And I guess next week is our last. I guess we'll have our discussion Friday, and I'll have the last homework posted by then so we can talk about it. I think I'll just have you calculate the band structure of silicon using the localized orbital stuff, just so you can see that it's really real and works. You can generate your own silicon band structure. So I guess that's it. We're out of time.
Why did you use free electron model in the quantum web?
Say that again?
Why did you replace K
With DDX?
Yes, because we are in quantum web.
Well, how else do you get something that's spatially, dependent, a function of position?
Yes, but we are in the quantum web. We can use the free electron model. You consider P as H bar K, yes? So
What if I have a quantum well with band bending like this? I want to be able to, in general, deal with potentials that are a function of position.
yes, but you replace K with a derivative.
Yeah.
And you can do it just for linear dispersion, not in the quantum web.
I'm not sure what you mean. You can just do it with linear dispersion, not in the quantum well. I'm showing how to do it here, and I'm doing the easy. What the heck? I'm doing the easy one because you also have to do it. Right? You also have to do it for this. And this starts to really give you a headache when you look at this. Wherever you see a K sub x in here, you have to replace it with ddx and discretize.
What I think is valid for linear time structure.
Why do you say it's valid for linear?
Because if we multiply it by H bar, we get an operator P, yes? So you consider P as H bar K.
Right.
So it's valid for linear.
Why isn't it valid for...
It's valid for free electrons, yeah? Cannot.
If I replace... Okay, I'll try it for free electrons. Sure. Challenge me. Okay, here we go. So free electrons. I've got h bar squared, k squared over 2m, right?
Yes.
And so I'm saying, okay, replace, wherever I see a k, replace it with, what did I say? K goes to minus I ddx, right?
Yes, because P is H bar K here.
Yes.
But when we are in the quantum, well, we cannot use it.
So, wait a minute, why are you saying that? I mean, if I get minus h bar squared over 2m d squared dx squared, right?
Yes. And it's valid for free electrons. And we are in the quantum and we can, our energy dispersion is like h bar to k dot over 2m, which k is np over a. It's not.
But this is a Hamiltonian. This is a generic Hamiltonian, right? I can solve this in a quantum well, right? This Hamiltonian works in a quantum well. H bar squared over Tm d squared dx squared. Now you just have to apply boundary conditions and you get your bound state. I mean, this Hamiltonian is fine for, right? This is just p squared over 2m. And now I discretize it and I solve it numerically. I mean, it's what we did when we, initially just started off with writing down p squared over 2m and discrete, so that's equal to what? Minus h bar squared over 2m d squared dx squared in 1d, right? And then we discretized it using finite difference. And we got, and then you put it on a grid. And that's when you get this dispersion in, if you do it in infinite space, E is minus 2t 1 minus cosine Ka. And if you do it in a quantum well, you're going to get your nice, if you discretize it with hardwell boundary conditions on some grid, you'll get your wave function that is, you only have it at discrete points, but it follows that normal envelope you'd expect in a quantum well.
Well, that's true, but I'm saying that d over dx here is not okay.
What's that?
D over dx here is not okay.
Why not? Looks like it's my k. I got a k squared term and a d squared dx term. D squared dx squared term. I just followed my recipe. One goes into the other, right? And that Hamiltonian is good for a quantum well, right? You're saying that k squared goes from there to there, no problem?
I mean, that's the equation. I think it's not true.
I'm saying it's a recipe. Do that recipe, right? You go from here to here, and that is your Hamiltonian you start with. And this is a Hamiltonian that's the exact Hamiltonian. It gives me whatever I need. So at any rate, this is a recipe that's used. Okay? And you can kind of play around with it and see whether you like it or not. But this is the way it's done. So if you want to model a laser, if you go back to the article by Gershoni, you can see it. And, this is what we've done to use the K dot P Hamiltonian and to model like transistors, or, the potential as a function of position. Nanowires, where you have confinement in the XY. So my poor student, who's now at Intel, he took this Hamiltonian and he modeled a quantum wire, which means FET, which means he had to discretize every K, KX, KY, and KZ, and put it on a three-dimensional grid. Now, if that doesn't give you a headache thinking about that, to put that on a 3D grid, and that's what he did, to model nanowire FETs using this K dot P Hamiltonian.